All right, today we're going to take notes over ecology. So, this is the study of ecosystems and in our interactions with it, but we're going to focus more on animal interactions as opposed to human interactions today. So, take three notes on the video that's about to play. Not the video Mr. Moore's talking in, but the video that's about to pop up. See that video that just popped up? Take three notes on this one right here.
We all know about the dinosaurs that once roamed the planet, but long after they went extinct, great beasts we call the megafauna lived on every continent. In the Americas, ground sloths the size of elephants pulled down trees with their claws. Saber-toothed cats the size of brown bears hunted in packs, but they were no match for short-faced bears which stood 13 feet on their hind legs and are likely to have driven these cats away from their prey. There were armadillos as big as small cars, an 8-foot beaver, and a bird with a 26-foot wingspan. Almost everywhere, the world's megafauna were driven to extinction, often by human hunters. Some species still survive in parts of Africa and Asia. In other places, you can still see the legacy of these great beasts. Most trees are able to re-sprout where their trunk is broken, to withstand the loss of much of their bark, and to survive splitting, twisting, and trampling, partly because they evolved to survive attacks by elephants. The American pronghorn can run so fast because it evolved to escape the American cheetah. The surviving animals live in ghost ecosystems, adapted to threats from species that no longer exist. Today, it may be possible to resurrect those ghosts, to bring back lost species using genetic material. For instance, there's been research into cloning woolly mammoths from frozen remains. But even if it's not possible, we can still restore many of the ecosystems the world has lost. How? By making use of abandoned farms. As the market for food is globalized, infertile land becomes uncompetitive. Farmers in barren places can't compete with people growing crops on better land elsewhere. As a result, farming has started to retreat from many regions, and trees have started to return. One estimate claims that 2/3 of land in the US that was once forested but was cleared for farming has become forested again. Another estimate suggests that by 2030, an area in Europe the size of Poland will be vacated by farmers. So even if we can't use DNA to bring back ground sloths and giant armadillos, we can restore bears, wolves, pumas, lynx, moose, and bison to the places where they used to live. Some of these animals can reshape their surroundings, creating conditions that allow other species to thrive. When wolves were reintroduced to the Yellowstone National Park in 1995, they quickly transformed the ecosystem. Where they reduced the numbers of overpopulated deer, vegetation began to recover. The height of some trees quintupled in just 6 years. As forests returned, so did songbirds. Beavers, which eat trees, multiplied in the rivers, and their dams provided homes for otters, muskrats, ducks, frogs, and fish. The wolves killed coyotes, allowing rabbits and mice to increase, providing more food for hawks, weasels, foxes, and badgers. Bald eagles and ravens fed on the carrion that the wolves abandoned. So did bears, which also ate the berries on the returning shrubs. Bison numbers rose as they browsed the revitalized forests. The wolves changed almost everything. This is an example of a trophic cascade, a change at the top of the food chain that tumbles all the way to the bottom, affecting every level. The discovery of widespread trophic cascades may be one of the most exciting scientific findings of the past half-century. They tell us that ecosystems that have lost just one or two species of large animals can behave in radically different ways from those that retain them. All over the world, new movements are trying to catalyze the restoration of nature in a process called rewilding. This means undoing some of the damage we've caused, re-establishing species which have been driven out, and then stepping back. There is no attempt to create an ideal ecosystem, to produce a heath, a rainforest, or a coral reef. Rewilding is about bringing back the species that drive dynamic processes, and then letting nature take its course. But it's essential that rewilding must never be used as an excuse to push people off the land. It should happen only with the consent and enthusiasm of the people who work there. Imagine standing on a cliff in England, watching sperm whales attacking shoals of herring as they did within sight of the shore, and until the 18th century. By creating marine reserves in which no commercial fishing takes place, that can happen again. Imagine a European Serengeti, full of the animals that used to live there: hippos, rhinos, elephants, hyenas, and lions. What rewilding reintroduces, alongside the missing animals and plants, is that rare species called hope. It tells us that ecological change need not always proceed in the same direction. The silent spring could be followed by a wild summer.
All right, so make sure you have 3 notes on that video. It was long enough to have more than 3 notes because it's 5 minutes long. It should have been 5 notes, but Mr. Moore's awesome, so he's gonna let you guys only do 3 notes. So this is the sun. I'm gonna mute this video while we talk because it's not really a exciting video. But I want to tell you that the sun is the source of almost all energy on the earth. About 99.97% of all energy that is on the earth comes from the sun. The 0.03% that we're talking about comes from actually vents in the bottom of the ocean. It's pretty cool that a whole ecosystem runs off of a vent that's on the bottom of the ocean, but a vast majority of all energy is going to come from the sun and through plants and other organisms that do photosynthesis, as we've learned earlier this year. Start the food chain and go from there.
Must be awful to be other kinds of stuff. You know, I'm glad I'm this. This is a pretty good deal when you consider the alternatives. Anything else, any other kind of thing, you're in the food chain. You're in the food. We are out of the food chain. I don't know if we fully appreciate the fact that we got out of the food chain. That is a massive upgrade. Because for every other living thing, life ends by being eaten. That's how all life ends, is every single life except human life. Every life ends like this. Ah! 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 We're the only ones that get to just die old in a bed. Just, I love you. I mean, imagine if we were still in the food chain on top of everything else. Imagine if we were in the food chain. It would just be another thing you got to deal with. You're already having a bad day.
All right, so as you mentioned a few times, the food chain. A food chain is a connected feeding relationship within an ecosystem. So we're talking about literally one chain link. We're talking about grass is eaten by cows and cows are eaten by humans. A population is members of the same species that live in the same area, okay? It says live in an area, but they have to live in the same area. So a population could be like this classroom. We're all human beings and we're all in this classroom. But Mr. Cooper's classroom is not a part of our population. He's a different population entirely. It's just us, and then Mr. Cooper has a classroom population. Now, if we increase the area to the 400 hallway, we would include classes like Miss G's, Mr. Cooper's, Mr. Reynolds, Miss McCormick's, so on and so forth. But when we're talking about just this classroom, we are members of this population. They are members of the other populations in this hallway. Community is a group of populations. So now we're including the spiders that are in this classroom, because there's definitely spiders and cockroaches and moths and all sorts of fun things that we don't see every single day, but they're a part of this classroom. Or if we talk about, and we look out our window here and look down into the courtroom, there's a population of trees, there's a population of grass, there's a population of bushes, there's a population of fish, and they're all in the same community because their area is the courtyard. And then finally, ecosystems. Ecosystems now includes all the non-living things as well. So now we're talking about the water that's out in the courtyard, or the rocks, or the concrete, things like that that are non-living. The soil are now included with the things that are living, like the fish, the plants, or the bushes, the trees, the grass, so on, so forth. Types of organisms.
Eventually, They have to go for
Uh-oh.
it.
We're going to stop this one up here because it's just grass growing. I'm not going to pretend like it's something exciting.
Eventually, they have to go for it. They have.
My goodness. This is such a pain in the tuchus. We're almost done with notes, kind of. See if the grass will grow for us. There we go. I'll mute that one.
Eventually,
We'll watch the
they have
bears
to go
down
for
here.
it, regardless of the danger.
Got him. Got him. Got him. Strike.
But numbers are on their side. For every salmon that gets caught, hundreds make it past the bears.
All right. So autotrophs are what we have up top. Autotrophs are things that create their own food or their own energy, and they use light. So these are things that are going to do photosynthesis. We know about photosynthesis. These are like plants and bacteria that are going to do photosynthesis. So for example, we're going to say most plants. Heterotrophs are organisms that cannot produce their own food. So like the bears and the fish down here, they have to eat something else. They can't just get their food from laying out in the sun. They're not plants. Like you and I, we can't just go sunbathing and be like, man, I'm so full because I so totally photosynthesized. Not realistic. Can't do it. Won't do it. Okay? So the example here is the grizzly bear. We have to eat something else to get our energy. How do organisms get their nutrients? See this grass sowing and growing. We're going to just mute that. All right, this is a little mousey eating some grass. Okay? And then finally we have whatever this is. Oh, decomposers. The same little mousey that's eating the grass has died and now gets decomposed. All right, so producers are animals that are going to go ahead and make their own food from light. Okay, so autotrophs and producers are almost interchangeable words. Okay, our example is grass. Consumers are organisms that eat producers or other consumers. For example, like the mouse eats the grass, but like a lion would eat a gazelle, and gazelle eats the grass. Decomposers are organisms that break down dead or decaying plants and animals. They just kind of eat dead things, and that's why like recycling happens. Decomposers typically don't have stomachs to digest, so what happens is they digest on the outside, they secrete enzymes that digest their food, and then they absorb the nutrients through the body. And what this does is it actually puts those nutrients, some of those nutrients, back into the soil for plants to grow. So it's like a cycle. If these three things didn't work together, none of them would really be able to eat. So it's pretty cool. Three types of consumers. First, we have a bunch of cows. That means none of this is going to work. Okay, let's try again. Come again. Three types of organisms. We got cows that are eating grass. So exciting stuff. Then we have lions. I'm going to speed this up. And a little buddy cow. You should watch this cow. It's going to be awesome. He sees you. Oh, it's all over. It's all over but the crying. And then finally we have humans. Oh, my friend Kobayashi. Look at the girl in the background. Hilarious. She picks her nose in one of these. Right here. This chick. Oh, there it is. Okay, she scratched the outside of it, but it's funny. That face, though. All right. So there's three types of consumers. We have the ones like the cows up top. They're herbivores. They're only going to eat plants. Then we have carnivores that are only going to eat other animals. We call these meat eaters. Okay? But they're carnivores. The example is lion. And then omnivores, organisms that eat both plants and animals. The example is not going to pop up, but it's down there. The example is humans. Humans eat only plants and animals. Other examples are like bears. They'll eat plants and animals as well. Like we saw in the first video, we see that bears ate berries, but they also eat salmon. So they eat both plants and animals. Dogs also do the same thing. Ha ha ha! All right. And last but not least, our final slide of the day. These are types of interactions. We're going to listen to my friend Mary Poppinroth, an adjunct professor from the University of Hawaii, I think.
Hi, my name is Mary Poppinroth. I'm an adjunct professor of biology, and today we're going to be talking about interspecific interactions. Interspecific interactions is an interaction between two completely unrelated species, and they fall into three categories: mutualism, commensalism, and parasitism. Now, in each of these interactions, you're going to have two species. In our example, we'll say species A and species B. So let's make a little chart, just to make it easy. For our chart, you're going to make one column for species A and one column for species B.
Create this chart.
If the interaction is positive for that species, you're going to put a plus. If it's negative, you're going to put a minus. And if it's neutral, you're going to put a 0. Let's start with mutualism. Mutualism is an interspecific interaction between two unrelated species that both species are going to benefit. Let's use the example of bees and flowers. Now, bees are going to get pollen and they get nectar in order to survive. And flowers benefit by getting the bees to pollinate themselves, as well as taking genetic information from other individual plants. Let's move on to commensalism. Commensalism is a positive for species A and a 0 for species B. That means no benefit, but no harm either. A real-world example of this is anemone fishes and sea anemones. You remember Little Nemo? Well, those anemone fishes get a benefit. They get protection from the stinging cells of the sea anemone. The sea anemone is not hurt or benefited by this interaction, though. Now, parasitism, we're going to write a plus for species A and a minus for species B, because in this type of interaction, one species benefits while the other species is harmed. Now, in parasitism, we see examples all over the place, many that we have to deal with each and every day, things like lice and bed bugs. So next time you're out in nature, look around. See if you can find other examples of two completely unrelated species interacting with one another. Thanks for watching, and if you want to learn more about this subject, click on the link below. Or if you want to learn more biology, feel free to click on any of the links around me. And please, rate, comment, and subscribe to this channel. Or maybe, if you have ideas for more videos, send us an email at requests@mahalo.com. Thanks for learning.
All right, so make sure you got that chart written down. Write down these definitions, and you're going to see these in nature when you're walking around, okay? The one species benefits, and the other one just is unaffected. You're going to see it when both species benefit, and you're going to say parasitism. I'm not going to rehash everything she said. If you need to go back and listen to her, go back and listen to her. Make sure you have that chart on your notes today. Has to have it for you to get all your points. And that's the end of our notes for today. Make sure you're bringing them up, showing them to me so I can give you some credit for them. And then get to work on the next assignment. Thanks.